Okay, let's take a look at some trends in boiling points and try to make some sense of it. Let's take a look at these four substances here first. Every one of them involves a central atom with two hydrogens surrounding it. And we're going down the periodic table, OCDPO, from oxygen to sulfur to selenium to tellurium. So we're getting bigger in mass. And generally, as the mass increases, the boiling point increases a little bit. So these are the boiling point temperatures here. But this one's a big outlier. Why? Because it can hydrogen bond. Similarly, none of these substances can hydrogen bond. I don't see any hydrogen covalently bonded to oxygen, nitrogen, or fluorine, whereas you do there. And so the trend should be simply based on molecular weight as we go from CH4 to Cussy-Gessen-Pub, right? From carbon to silicon to germanium to tin and presumably to lead as well. The boiling points increase with the molecular mass. I believe the argument is that there's more polarizability for the larger ions, so you can get a greater difference in electronegativity between the two molecules. So you have a little bit more plus minus going on for the intermolecular force, and it becomes a little stronger as a result. It has more ionic character. Here's another trend. Let's do the red ones first. So we have NH3 to PH3 to ASH3 to SB, NPASB, NPASB, nitrogen, phosphorus, arsenic, and antimony. And as the same trend follows, as the molecular weight increases, the boiling point increases. However, this one is a big outlier. Why? Hydrogen bonding. The H to N bond exists here covalently, so it can form an intermolecular hydrogen bond, which should be relatively strong. Wonderful. It looks like we're going to see the same thing here. H to F to Cl to bromine to iodine. And so for these halogens, the molecular weight is increasing, and the same thing happens. You see an increase in boiling point as it goes from chlorine to bromine to iodine, but it jumps up here because of the hydrogen to fluorine covalent bond makes hydrogen intermolecular hydrogen bonding possible, and you get a big jump in the boiling point there. And so that's how we can rationalize these boiling points using intermolecular forces. And note the big effect of hydrogen bonding. Beyond that, it's a molecular weight comparison as long as it's apples to apples. It would be difficult to make guesses between these kinds of substances.